All right, class, let's go ahead and finish up the lesson on exponentials. Okay, so this is section 3.2, which deals with exponentials, part 2. So we're just going to kind of go a little bit more in detail, maybe kind of clear up any confusion. Hopefully, this will help a little. I just wanted to give you an example. This is an example of an exponential. Okay, this is an exponential growth. And this one down here, this is an exponential decay. But anytime you see that curve, those are exponentials. Okay, they start out low at the beginning and then they rise, or they start out really high and then they curve down and approach zero. Okay. This one here is just kind of showing you like the first 5 hours. Okay, this is how much it grew. I think it's about 60,000. I think this is about 60,000. If we could actually go over here, but let's just say it's about 60,000. It took 5 hours to get to 60,000. But what happened? So it took 5 hours to reach the 60,000. But what happens in the next hour? In the next hour, now it only takes 1 hour and it's already at another 60,000, but at least this distance is 60,000. So it takes a while to get going, but once it gets going, it approaches very, very quickly. Okay, the next 60,000 would probably be, you know, even maybe even a half hour. Okay, so once it gets going, it starts then rising very quickly. Okay, that's what that's saying. This one's kind of showing the same thing. This is a line, right? We know this is a linear. Look, the line even starts off higher. So the line starts off more. But right here, the line doesn't even come close. Once, same thing as up here. Once that exponential gets going, there's like no stopping it, right? Now it's significantly more, and it's only going to get a bigger separation between the line and the exponent as we go out. So linear is kind of like the turtle, slow and steady, right? But the rabbit, once, you know, maybe it was slow at first, but once it gets going, it grows very rapidly. Okay, so that's that guy. Let's just take a look this real quick. This just says tell if it's exponential, linear, or neither. Okay, so this straight line, this would be linear. Okay, this, what is this guy? This is the nice curve that starts high and comes low. This is your exponential. I don't know if I have enough room, so I'll just do EX for exponential. This one, you know, it kind of dips around. There's a little bit here, but there's too much. If it changes direction, something like that, this is not by itself an exponential, so this is neither. Same thing with this. This comes up, this is maybe more like a parabola, but this is not, this is neither. It's not linear, and it's not exponential. Okay. This we definitely know, that's a circle, right? So that is neither. And then this one, very straight, that is a line. No curve to it at all, that's a line. Okay, so now one thing, and we're going to write this down in a minute, one thing that gives away that you have an exponential, something, if you know you have an exponential, there's a constant percentage. There's a constant percentage. But our author wants us to take a look at some of this word as well. What happens if something is doubling? Okay, so I just came up with an example. You can do any number that you like. I just said, okay, let's just use the example. This is example 12. Okay, if 12 doubles, what does that take us to? If 12 doubles, that takes us to 24. Okay, now I want to come up with a percentage rate. I'm going to use the very first equation we learned in this class. I'm going to do end minus beginning divided by beginning. That gives me my percentage. Increase. All right, so 24 minus 12 divided by 12. That gives me 12 over 12, which is 1. As a percentage, I move it 2 places this way, and that's 100%. Okay, so doubling is the same as 100% increase. And if it's 100% increase, then it's exponential. So this is kind of a way to hide the percent. Doubling is 100%, and doubling we usually think of like 2. In fact, doubling is the same as 2 times. But notice the relationship with the percent is only 100% increase. But a percentage increase deals with exponential. Okay, and I just came up with these numbers randomly. I left enough room if we want to do another example. Like, does that hold true all the time? Like, let's say I start at 8 and head to 16. Now, how come I went from 8 to 16? Well, that's double, right? Doubling 8 would take us to 16. If I use my percentage increase formula, end minus beginning divided by beginning. Gives me 8 over 8, which is 1. As a percent, that's 100%. I move it 2 places to the right. Okay. All right, let's take a look at tripling. What do we think tripling? Tripling is 3 times. Okay, but we said that exponential usually deals with a percentage. So does tripling and 3 times, is there a percentage hidden in there? So I just said, okay, let's do example. Let's just come up with a number. Let's do 12. What is 12 tripled? 12 tripled is 36. All right, so let's use our percentage. End minus beginning divided by beginning. 36 minus 12 divided by 36. Or, sorry, no, wait, divided by beginning, right? Divided by 12. Sorry about that. Divided by 12. And these two should be the same. So divided by 12, that looks better. 24 divided by 12 gives me 2. And as a percent, 200%. Okay. Tripling 3, notice the percent is only 200, and that's okay. That's just the relationship there. But tripling does mean that there is a percentage, which does mean that you have an exponential. Okay. And you could try this with any number. You don't have to do 12 and 36. I just made these up. That's why I called it an example. If you take any number and triple it, but then you put it into our formula, it's always going to be 2, which gives us 200%. Okay. Let's do that one more time for quadruple. Okay. Quadruple is what? 4 times. Right? Let's see, is there anything else? Okay, so quadruple, let's just stick with our example, though we could change it if we wanted to. I just stuck with 12. 4 times 12, or quadrupling 12, takes me to 48. Okay, does anyone want to guess? What percent do we think? If 2 times was 100%, 3 times was 200%, what do we think 4 times is? But let's try it. Let's do end minus beginning. Make sure I divide by beginning. Okay, that gives me 36 over 12, which gives me 3. As a percent, 300%. Okay, and we're going to come back to this one more time. Maybe even a couple more times. But so it's just quadrupling 4 times. It's only 300%, but because it is a percent, it's exponential. Okay, so is a population size an exponential function of time? Yes. Okay, because it is a percent. Percent means exponential. If you see percent, you're thinking exponential. Okay, yes, because, let's write this, because quadruples is a 300%, but basically because it is a percent. Okay. All right, so keywords that show exponential function. I just wanted to notice, or just make a note. Exponential function deals with a constant percentage. Okay, exponential function deals with a constant percentage. You got to remember that. But don't forget the word doubles, or even the word, the phrase 2 times is really a percentage, right? It's 100%. Okay, same thing with triple, right? Triple is 3 times, which is a percent, and a percent means it's exponential. So these words also mean exponential because in it, hiding is a percentage. Okay, We could do quadruples is 4 times, okay, which is 300%. The key thing is that percent. Hiding in doubles, triples, and quadruples is a percent, so that means it's exponential. Anything past that, then we usually just say the times. So you could put in the blank times, okay? So an example would be like 7 times, but it's kind of like fill in the blank, right? 7 times, what would 7 times be? 7 times would be a 600% increase, but as long as we're talking about a percent increase, it's exponential, okay? All right, this one gets a little big, but let's just try it. This one's a little crazy. The fish population in a pond triples every year. What is the constant percentage increase each year? So triples, we have to remember that triples actually means it's only a 200% increase, okay? Triples goes down. These three always stay the same, and then kind of once you get that pattern, you can apply it to any other number that you put in there. Okay, if there are 150 fish in 2015, how many fish will be in the pond in 2025? So we know because it's triples, it's a percentage. As soon as there's a percentage, y equals I, 1 plus r to the x. Every single time. It's either y equals mx plus b if it's linear, or it's y equals I, 1 plus r to the x. This is a power if it's exponential. Those are the two things that we have so far. Okay, so y equals, what's my initial value? 130 fish. What is my rate as a percentage? I move it 2 places, so that goes back to 2. Okay, and here now you can see where the tripling comes in, right? Because that's actually now going to change to 3, which then correlates back to the triples. Okay, x is how many years? From 2015 to 2025? That's 10 years. Okay, so here is, now you can see where the tripling comes in, because that's a 3. Okay, and this number is quite large. Okay, but remember, that's what exponential does. So this gives us, I think it's 7,676,370. Okay, and that's what our book also talks about. Maybe, you know, this equation doesn't hold true past 4 years. So they always say, keep in mind how many years is your model realistic. So taking a look at this, it might not be realistic, but at least that's what it is predicting. That's what this equation is predicting for 2025. Okay. All right, let's take a look. This is similar. One last thing, or these two kind of go together, and then we'll move on. Only a 1/10 of the population. This is kind of like the reverse of doubling or tripling, okay? Only a 1/10 of the population remains. That's not very much, right? But kind of the same thing. So I just started with an example. I said, if I'm talking about 1/10, why don't I choose something easy? So I said, if I start out with 100, only a 1/10 is remaining. So a 1/10 of 100 is 10. Okay. Population is declining. Each year, only a 1/10 of the last year's population remains. What is the constant percentage decrease? So hiding in here is a percentage. If a hiding in there is a percentage, then we do have an exponential. Okay. So let's take a look. What would this percentage be? End minus beginning divided by the beginning. So it would be 10 minus 100 divided by 100. Okay, so that gives us negative 90 over 100. Right? So that gives us negative 0.9. Now what is the negative? The negative is just talking about it decreasing or declining. So this is the decreases. Okay, that negative is just decreases. Let's change it to a percent. 1, 2, so 90%. Okay, now let's put in the negative because it's actually decreasing. Okay, but the negative is there because it is a decreases by 90%. Okay. If the question on the homework says decreases by how much, then we probably could just write the 90%. All right, let's take a look. One last one here. From 1914 to 1919, America's trade with the Netherlands colonies increased by approximately 1,300%. How many times bigger was the 1919 trade amount than the 1914 trade amount? Okay, so this is a huge percentage, but what they're getting at is, remember, 2 times the percent was only 100. Okay, 3 times or tripling, right? Oops, let's just write 3 times, but triple, it was 200%. Okay, quadrupling 4 times was going to be 300%. Okay, so we could go, let's go to 9 times. 9 times, what would the percent be? 9 times the percent would be 800. Right? This number goes down 1, but this time we actually have the percent. So if this is 1,300%, and notice you just focus on this number, what if it's 8, then it's actually 9 times. So here we were actually given the percent, 1,300%, just take the 13, and that would actually go to 14 times. So our answer is 14. Okay, but they just kind of wanted you to get the relationship between how many times and the percent. This way it's down 1, this way it's up 1. Okay. Okay, this here is just, do I want y equals mx plus b? Is it a linear function or is it an exponential function? Okay, that's all they want there. And note, for linear function, you would use y equals mx plus b. For an exponential function, you would use y equals your initial value, 1 plus r, and x is an exponent. Okay, so let's try to figure out which one of these they are. Okay, you drink a beverage with caffeine in it. Each hour, the amount of caffeine in your body decreases by 12%. If it decreases by 1%, that's your exponential. Okay, and for this, we don't have to do it each time, but for this problem, we would use this equation. Okay, your car travels 60 miles every hour. Every mile, you're adding another 60. If you're simply adding a number every hour or every interval, then that is linear. Okay. All right, the number of cell phone owners from 1988 to 1997 tripled each year. Okay, so tripled, what's hiding in there? What's hiding in tripled? That's a percentage. A percentage means you have exponential. Okay, so if I was going to do anything more with this problem, if they told me a little bit more with this problem, I would use this equation. Things are tripling, that's a percentage, that's exponential. Okay. The isotope known as carbon-14 has a half-life of 5,730 years. Half-life is automatically exponential. Okay. All right, how about this one? A baseball team scores 3 runs every inning. Every inning plus 3. Every inning 3 more. If it's adding on, what is adding on? If it's adding the same amount each time, that is linear. Okay. All right, let's take a look. We got a few more. Last page here, guys. Okay, we're doing really good. All right, how about the mice population is getting 7 times bigger every 2 years. The mice population 7 times bigger. Times, what's hiding in a 7 times? A percentage. Okay, as soon as we're talking about a percentage, exponential. Okay, 7 times, what's hiding? In fact, what percent? You tell me what percent is hiding in 7 times. Okay, if it is 7 times, 600%. Okay, let's look at our chart here. Remember, the times, the percent goes down by 1. If we're going this way, the percent goes down. If we're going this way, then it goes up. But in a 7 times, a 600% is hiding. As soon as it's a percent, it's exponential. Okay, Joe's bank account grows by 5% every year. As soon as it's percent, exponential. Okay. Now, what about Susan? Susan's bank account grows by $400 every year. So every year, what am I doing? I'm adding 400 every year. If I continually add the exact same amount, that is linear. Okay, so kind of compare these two. His grows by a percent, that's exponential. Susan's grows by just a value, that's linear. Okay. Okay, here we go. Last one. The deer population has a, this should say a growth rate. Sorry, that should be a growth rate of 2.1% each year. As soon as it's a percent, exponential. Okay. All right. Let's take a look. This whole thing, this last one is one problem here. It might help to have a little calculator. Here we go. All right, suppose you start work for a company at age 30. You are offered 2 rather unlikely retirement options. Retirement option 1, when you retire, you will receive $15,000 for each year of service. Okay. Retirement 2, you will start work, when you start work, the company deposits $2,000 into a savings account that pays a monthly rate of 1.3%. When you retire, the account will be closed and the balance given to you. Okay, so which is better if you retire at age 63? Okay, so option one, every year you get $15,000. That's the same amount each year. That is linear. So this is y equals mx plus b. 15,000 times the number of years. So this is going to be 15,000 times x. Okay, and actually you start out, remember b is actually 0. Okay, if you don't work anything for them, they're not going to give you anything. So the plus b is where you start, and you're actually starting at 0. So there is no value there. You're just literally doing 15 times the number of years of service. Okay. So how many years of service are there? Between age 30 and 63, there are 33 years of service. So 15,000 times 33. Okay, this is linear. Y equals mx plus b. The plus b is 0, so you don't even need that. Okay, and so that should give you 495,000. Okay. All right, option 2. Option 2 is a percent. So as soon as I see a percent, I'm going to y equals I1 plus r to the x. Okay. So my initial value, they're going to give me 2,000. 1 plus this as my percentage as a regular number, move a percentage as a decimal, 2 places to the left, 0.013. Okay. Now this is where it just gets a little tricky. This x is monthly. So yes, I'm working for 33 years, right? 33, but I have to do 33 times 12. I have to take it times 12 because this is years and I need to put it in months. So 1 year would be 12 months. 2 years would actually be 24 months. 3 years would be 36 months, okay? What is 33 years? 33 years, so 2,000. I might as well add these together. So I'm just going to write this as 1.013. 33 times 12 is 396. Okay, so that's the only tricky part. This 12 is because it deals with monthly. Okay, but even after that, I get 332,943. If we want to add on the cents, 36 cents. Okay. So which option's better? Option one, right? Option one, I'm going to get at least some more money. This is almost 500,000, right? This is closer to 300,000. Okay. All right, but what happens with exponentials? They start out slow, but once they get going. So let's see what happens if we work all the way to 71. Okay, so option one is still linear, 15,000x. Okay, but this, how many years is it now? From 30 to 71, that should be 41 years. So 41, okay, 30, 40, 50, 60, 70, and then 1. All right, so here, remember, this guy's slow and steady, so this gives me 615,000. Okay, all right, but option 2 is my exponential, so y equals I, 1 plus r to the x. Okay, my I is still 2,000, my initial value. My rate is still the same, 0.013. Okay, now I'm going to do 41 times 12. I still have to take it times 12 because I'm still doing monthly stuff. Okay, so I might as well, 2,000, I might as well change this to 1.013, and then 41 times 12 is 492. Okay. All right, what happens when I type this in? Remember, this is an exponent. Okay, when I type this in, I get 1,150,474. And of course, 81 cents. Okay, but remember, this guy now starts to be better and a lot better, right? It's not even close. Remember, so the whole point was to show you that linear starts off strong, but once that exponential gets going, there's no turning back. Okay, so at some point there might be like a break-even point, and then everything after that, not only is exponential more, but it starts rising really quick. All right, try your homework, see how you do.